Chapter 3, Matter and Energy. In this chapter, I'm going to introduce you to the definition of the matter. We're going to talk about atoms and molecules. And then I will talk about the state of the matter and physical and chemical change. And then we move to the classification of the matter. And then I will talk about energy, different types of energy, definition of energy, heat, specific heat capacity. And at the end, I will do examples regarding heat and specific heat capacity calculations. Now, let's start with the definition of the matter. Then what is a matter? Basically, anything that has mass and occupies space, or it has volume, it's a matter. Okay? And if you look at something, and you will see that it has mass, and it takes on volume, or it occupies space, it's a matter. Matters could be atoms, or it could be molecules. Now, what's the difference between atoms and molecules? Atoms are the smallest unit of the matter. Okay? Atoms are just one thing. Then if you look at this pink sphere, it's just one thing. That's an atom, which we could call it a hydrogen atom. Okay? It's just one thing. All right? Now, when two or more atoms join together, they make molecules. Molecules could consist of same atom, or they could consist of different atoms. Then, for example, if I go back to my hydrogen atom, as you could see here, there are two hydrogen atoms joined together. There are two spheres. That makes it to be a molecule, and we call it a hydrogen molecule, which is made of two hydrogen atoms. Okay, that's a hydrogen molecule. Now, in the other example, we have hydrogen, and we could have a different atom, like chlorine. Okay? Now, instead of the same atom, you have different atoms. One is hydrogen, one is chlorine. And that's hydrochloric acid. That's the name of this compound, HCl. And it's a molecule that consists of a hydrogen atom and a chlorine atom. Also, if you consider like water, okay, our drinking water, it's made of hydrogen, two hydrogen, and one oxygen. Okay, this is also a molecule. Okay, water, H2O, it's also a molecule. It's made of two hydrogen atoms and one oxygen atom. So this is the difference between atoms and molecules. Now, what are the state of the matter? State of the matter includes solids, liquid, and gases. Now let's talk about solids. Solids have definite volume, and they also have a definite shape. That means they maintain their shape regardless of the container they are placed in. Then if you consider your pencil, if you put it in a glass, or in a big jar, or in your pencil case, it keeps its shape, maintains its shape, no matter where you place it in. Also, solids, they have a regular pattern. Then if you look at the example here, if you look at the molecules, you see they repeat themselves. They have a regular pattern. Okay, because the particles, first of all, they lie close to one another, and that makes it having a regular pattern. Then one more time, solids have definite volume, they have a definite shape, and they also have a regular close packed structure. Okay. Now, liquid. Just like solids, Liquids have a definite volume, but they do not have a definite shape. Okay? They take up the shape of the container they are poured in. Assume some water, liquid water. Put it to different size glasses, different shape glasses. It take up the shape of the container it's poured in. Okay? Then liquid, they have definite volume, but they do not have a definite shape. And also look at this shape or this pattern for liquid. Then if I go back to solids, you see how the patterns, they have a regular pattern, solids. But now let's look at the liquids. Liquids, they do not have irregular patterns. Okay? That's why liquids, they can move past one another. Okay? And that's the difference between liquids and solid. Last one, gases. Gases, they do not have a definite shape or a definite volume. Then they do not have a definite shape because they take the shape of the container they are in. Also, they do not have a definite volume. They assume the volume of the container they're inside. And as you could see in this example or in this picture, gas particles are so apart from each other. And that's why they move at a random motion, because they're so apart from each other. The intermolecular forces between gas particles is so weak. And that contributes to them not having a definite shape and volume. All right. Now, let's talk about physical properties. Then physical properties could be observed or measured, okay, without changing the composition of the material. Then that's the key when we are talking about physical property. For example, you could check the color, the odor, the state of the matter, melting, boiling, solubility, without changing it. Okay, for example, if you are looking at the color of your pen, my stylus pen is burgundy. By looking at it, my stylus pen is not going to turn into an eraser. Okay, that's a physical change. Okay, it remains as is. The composition of the material will not change. Okay, that's an example of physical property. Then if you look at this example, here we went from solid water, which is ice cube. Solid water is our ice cube. You're gonna heat it up. This little triangle means heat. And it's gonna become liquid water. And then you're gonna heat it further and it becomes gaseous water. Okay? Water vapor, that's what it is. Then as you could see here, we started with water molecules, we end with water molecule. The only thing changed was we went from solid to liquid to gas. Only the state of it changed. The water remained the same. This is an example of physical change. Okay? That means the state or the actual composition of the matter remains the same. Or another way, whatever you start with, you end with that exactly same item or atom or molecule. Okay? That's the definition of physical change. Now, chemical change. One substance can be converted to another substance. Okay? Which means the composition of the matter will not remain the same. For example, you bought a very shiny bike in the summer. And for example, assume you're living in Seattle that rains a lot. You leave your bike outside for the whole month, for the whole fall winter season. And you go back to it in spring. It's not that shiny bike anymore. It's all rusty and ugly and oranges. It doesn't look that new anymore. Then what happened here, we had a process of rusting, which means your beautiful bike that's made of iron, it reacted with oxygen in the air and it became iron 2 oxide. Okay, this is the rust. Okay, that's what happened. And I'm going to add these coefficients which are later on just to balance it out. You don't need to worry about this. We talked about it. But all I care about right now for you guys to know is that I started with this iron, which is your nice shiny bike that you bought in the summer. You left it outside during the rain season. And when you go back to it, it's not that shiny bike anymore. That means iron has changed to rust, which we also call it iron 3 oxide. That's what it is now. Then as you could see, one substance, which was iron, was converted to another substance, which is iron 3 oxide. Then unlike the physical property or physical change, whatever you start with, do not end with that exact thing. That's the total difference. When we are talking about chemical properties, it's one substance convert to another substance. Oxidation, burning, rusting, these are all examples of chemical change. Okay. Another example of chemical change is when you go to a hairstylist and you bleach your hair. Okay, it causes change to your hair and the composition of your hair. That's also a chemical property. This is one of the examples of a chemical property. That's when hydrogen gas, let's write it here so that you can see it, reacts with oxygen gas, or hydrogen molecule reacts with oxygen molecules, and it makes liquid water. Okay. Then as you could see, we started with hydrogen and oxygen molecules. We ended with water. Are my starting material the same as my product? No, it's totally different. This is also an example of chemical change because one substance converts to another substance. That's a chemical change, and that's the definition of chemical change. Then when we are talking about physical change, we work with one item the whole time. Okay? But chemical change, one substance convert to another substance, which means whatever we start with is not the same as what we end with. Our end product is different, whereas in physical change, it will not be. Now let's talk about classification of the matter. Then we talked about matter. Anything that has mass and occupies space is a matter, right? Now, matters are classified into pure substances and mixture. Okay? Now, let's talk about the definition of pure substances and mixtures individually. Then pure substance is a single component. It could be an atom or it could be a molecule. Okay, it's just one thing. Like sugar on its own is a pure substance. Okay, sodium atom on its own is a pure substance. Okay, these are examples of pure substance. It's just one single item. It could be an atom, it could be a molecule. It doesn't matter as long as it's a single component that makes a pure substance. Pure substance, they have a constant composition regardless of their size, and you cannot break it down to other pure substances by a physical change. They do not undergo physical change. That means if you break it down, you will end with something different. Okay, then these are characteristics of pure substances. Pure substances are only one single component. It could be an atom, it could be a molecule, for example. It could be salt, which is NaCl, or it could be sodium atom on its own. Since it's on its own, it's one component, it's a pure substance. Then pure substance, they have a single or a constant composition, and you cannot break them down to other pure substances by physical change. Think about it. If you break down sodium chloride and NaCl, you cannot end with sodium chloride anymore. Okay? Or the same thing, if you bombard the hydrogen atoms, we will not end with hydrogen atoms anymore. Okay? Therefore, pure substances, they do not undergo physical change. These are examples of pure substances: sugar on its own, water on its own. On their own, they are pure substances. All the elements on the periodic table, on their own, they are pure substances. Now, mixture, they are composed of more than one component. Okay, they could have different composition. It could be a solid, it could be a liquid, it could be a gas. Okay, and you could separate them through physical processes. Then, as you can see, this is totally different from pure substances. Unlike pure substances, mixtures are more than one component. They could have different composition. Some part of the mixture could be solid, some part of it could be liquid. Okay, and they do undergo physical process or physical change. Now let's look at sugar dissolved in water. Then you have this beaker, you put some sugar, you add water. Okay, we add sugar, we added water, you heat it, and what you end up with is a sugar which is completely dissolved in water. Okay, none of us, all you have. This is a mixture, and your mixture has two different composition. It has solid sugar, which is a solid particle, and it has water. Water is a liquid state. Sugar is a solid state. Okay, then once it's heat up, you make your sugary water. Also, one other thing, consider you go to the beach. Right now it's just so nice and sunny and warm. You get a bucket and you fill it with water and sand. Okay, and this is sand and that's water. You don't want you want to separate the sand from water. Okay, then what you could do is you could use a funnel. Okay, you could use a funnel, and you could use a paper, filter paper, and you're gonna pour in the components from this beaker. Then you will end up with water down here, and you will have the sand particles collected on the filter paper. That's what I mean by the fact that mixtures, they could be separated into their component by physical process, which means I started with water and sand, I ended with water and sand. The only difference was that I separate them. It's not that I started with water and sand and I ended with like sodium and like salt and water. No. Then unlike pure substances, mixtures, do undergo physical change. And once they undergo physical change, which means whatever we start with, we end with that same exact components. Now, we have homogeneous mixtures and heterogeneous mixtures. Homogeneous mixtures are the same throughout. Okay. For example, if you go back to my previous example here, that I warm up the sugar and water, and you end up with a mixture, which means all the sugars completely dissolve in water. That's a homogeneous mixture. Okay, which means everything is the same throughout. Okay, or when you make your coffee in the morning, right, it's a homogeneous mixture. If you do a good job, your coffee machine is not broken. You don't see like water particle on one side, liquid water on one side, coffee grains on the other side. They're all mixed up. It's just the same throughout. It has the same composition. That's an example of homogeneous mixture. Like when you dissolve the salt in water completely, or when you go gas your car, the air around you. When you look at the air around you, do you see hydrogen gas on one side, oxygen on the other side, carbon dioxide at the end of the room? No, everything is mixed up. These are examples of homogeneous mixtures. Whereas for heterogeneous mixtures, they have more than one phase. Then if you recall my beach example, the mixture of sand and water, as you could see, then we have sand and water. That's a homogeneous, this is an example of heterogeneous sand. This is water. This is an example of heterogeneous mixture. Then as you could see, it has different composition. Sand particles are solid, water is liquid. Okay. Other examples is oil and vinegar. When you want to make your salad dressing, you have oil and vinegar. No matter what you do, no matter how many times you shake it a million times, still oil and water are separated. You cannot mix them. They are immiscible. Or our example, sand and water. Okay, no matter what you do, you cannot dissolve sand in water. Then these are the examples and definition of homogeneous mixtures and heterogeneous mixtures. Now let's talk about some separation techniques for mixtures. One is distillation. Okay, if you deal with homogeneous mixture, we usually use distillation. Okay, like if you look at this example, we have a mixture of salt and water. The salt is completely dissolved in water. Then what we do is that this system undergoes distillation. That means we heat the solution of salt water, then the water starts boiling at 100 degrees Celsius, and it goes through this tube. Okay, that tube, it's connected to cold water. Then cold water converts gaseous water or water vapor to liquid water. Okay, and that liquid water, which is a pure water, it will be collected in the other end, and at the end you will end up with salt left over into your flask, and in the other flask you have your pure water. Then usually, most likely, when we have homogeneous mixtures, we use distillation. Distillation works, it's based on boiling point of the liquid, or of the so based on the point of the solvent. Okay, here is water. Water boils up 100 degrees Celsius, and it passed through a cool tube, and it was converted to liquid and was collected. Whenever we have heterogeneous solutions like your sandy water or a liquid solid type separation, we use filtration. Okay, like this example, we have a funnel, we have filter paper, we pour the solution, our salt and water solution, through the filter paper, and we collect water here in the beaker, and at the end we will end up with solid particles, it could be salt, on the filter paper. Then filtration is another example of mixture separation. So now let's talk about classification of pure substances. Okay, the matter, it separates into pure substances and mixture. Pure substances are just one thing. It could be atoms or molecules, but they are only one thing. Okay, whereas mixtures, they are two or more components. Pure substances, they do not undergo physical change, whereas mixtures, they do undergo physical change. All right, now let's talk about pure substances. Pure substances are classified into elements and compounds. What are the elements? Elements is a pure substance that cannot be broken down by any chemical chain. Every single elements on the periodic table is an element. Okay, and you are responsible to know the name and the symbol of the elements on the periodic table. The list is posted on Canvas. Then every single element on that periodic table, it's an element. Okay, it cannot be broken down by a chemical change. Like the examples are hydrogen, oxygen, nitrogen, aluminum, carbon, and etc. Okay, now this is the list that I have posted on Canvas, and you will be tested on the name and the symbols of these elements on the periodic table. Okay, I will be tested. Probably by the time you get to this chapter, you've already been tested on these elements. Okay, then you could just practice on your own, just to make sure you still do know the name and the symbol of the elements on the periodic table. All right, now compounds, it's made of two or more elements. Okay, like sodium chloride. Then sodium on its own reacts with chlorine on its own, and it produces sodium chloride. Okay, it's our table salt. Okay, then as you could see, it's made of sodium and chlorine. Okay, or these pure substances, they join together and they make a compound. Okay, compounds are joined together through chemical bonding. We call that a chemical bond. Okay, that's how atoms or elements are bonded to each other, through chemical bonding. Then this is an example of compounds. Okay, they are joined together. They are pure substances that are joined together through chemical bonding. All right, now let's just summarize everything one more time. Matter, anything that has mass and volume is a matter. Matter is broken into pure substances and mixtures. Pure substance is just one component. It could be an atom or it could be a molecule. It's just one thing. Mixtures are two or more components. Okay, like we have a mixture of sugar and water. Okay, or sand and water. These are all examples of mixtures. mixtures, we have homogeneous mixtures and heterogeneous mixtures. If it's only one phase throughout, it's homogeneous. If it's two or more, it's heterogeneous. Now, one more thing, pure substances, they do not undergo physical change where mixtures do. Now, pure substances, they are classified into elements and compounds. Elements are just, it's just one thing, okay? It's just one atom, every single element on the periodic table. And you cannot break it down into any simpler substance because it's as simple as it gets. Okay, you cannot break it down anymore. Compounds are two or more elements. Okay, they are compounds. Like, let's see, aluminum on its own is an element, but aluminum oxide, it's a compound. Okay, it's made of two or more elements, and compounds are joined together through chemical bonding. All right, this is another way of classifying the matter. The matter, just look at it. If it undergoes a physical change, it's a mixture. If it not, it's a pure substance. Pure substances, ask yourself, can you break it down anymore? No. If you cannot, it's an element. If you could, it's a compound. Okay, that's another way of looking at it. Now let's talk about the law of conservation of mass. Okay, if you recall, when I was writing down chemical reaction, I put those coefficients, which I told you guys you don't need to know it. I did that to follow the law of conservation of mass, which I will talk about it in depth in future chapters, which you don't need to worry about it at all. All I want you to know right now is just to know the definition of the law of conservation of mass. Okay, then by definition, matter is neither created nor destroyed in any type of chemical reaction. Okay, and it says, based on the law, during any physical or chemical change, the total amount of the matter has to remain the same. Okay, that's why if I go back here, let me go back fast to one of these original slides. Oh, here, the bikes example. Remember, I added 2 in front of the iron 3 and 2. I just wanted to make sure, for example, on the left side I have 2 iron, on the right side, oh, actually that is not right. This is 4. I hope you fix it. I did that because I wanted to make sure I have the same number of each atom on each side. Then on the left side I have 4 iron, on the right side I have 4 iron. Again, on the left side I have 3 times 2, which is 6 oxygen. On the right side I have 6 oxygen. Then I did this balancing. I added these coefficients to follow the law of conservation of mass. That's why I wanted to have the exact same number of each species or each atom on each side of the equation. That's why matter is neither created nor destroyed. Then whenever you are writing down chemical equation, you have to follow the law of conservation of mass. And as I told you guys, I will talk about it in depth, and you don't need to worry about it for now. And basically, whatever we start with is whatever we end with. The number does not change. One example that I usually give is that you go to the grocery store, buy the ingredient for spaghetti or pasta, and then you put it all together. You cannot end up with like salad. Okay, that's one of the things. Or if you did not put mushroom in your pasta sauce, you cannot have mushroom in it. Okay, that's basically kind of the same thing. Basically, whatever we start with is exactly whatever we end with. Energy, by definition, energy is the ability to do work. What is work? It's the result of a force on a distance. Okay, then if you go from point A to point B, okay, first of all, you need to have energy. Okay, then I'm going to go from point A to point B. Then you're going to go from A to B. You need energy to go from A to B. Also, you've gone a distance. Okay, that's a distance, like X meter. This whole thing is called distance. Write it just as distance. Then in order for you to go from point A to point B, you've done work. Then you use the energy in your body. You went from A to B, okay, which we went through a distance, and you've done work. That's the definition of work. Laws of conservation of energy. Then the first law of thermodynamics, it says energy is neither created nor destroyed, which means the total amount of energy remains the same. Energy can be changed from one kind to the other kind, okay, but the total amount stays the same. It's kind of the same as the law of conservation of mass, okay. You cannot recreate or destroy mass. The total amount of the mass has to stand the same. Same thing with energy. Energy is neither created nor destroyed. The total amount of energy always remains the same, okay? But energy can be changed from one form to the other form. We have two types of energy. We have kinetic energy and we have potential energy. Kinetic energy is the energy of movement, okay? Electrical energy, mechanical energy, these are examples of kinetic energy. Potential energy is the stored energy, which is the chemical energy, which is the energy stored in battery. Then you go gas your car, then you add a fuel to your car. You start your car in the morning, then the energy from battery, okay, right, it goes to the wheels or to the engine. That means it went from chemical energy to mechanical energy. It helps you to move. Then as you could see here, the energy converted. We went from chemical energy to mechanical energy. Okay, that's what the fact we mean. Energy can be converted from one to the other. Okay, then you start your engine in the morning. The energy is stored in your battery, which is a chemical engine. Its chemical energy converts to mechanical energy and your car starts moving. We have different units for energy. Calorie is the amount of energy required to raise the temperature of 1 gram of water by 1 degree Celsius. That's the definition of calorie. Then you're going to rise the temperature of 1 gram of water by 1 degree Celsius. We use calories in food. Then if you buy these packaging food, it's the law that all the calories for the food has to be written. Then if you reverse the food packaging, you will see for a specific amount what is the calorie. And whenever we are dealing with food, we deal with calorie as a unit for energy. Joule is another unit for energy. It's actually the SI unit for energy. It's the one that's commonly known around the world. This is the conversion between calorie and energy. You don't need to know the number. If you need it, I will give it to you. Kilowatt hour is another unit of energy. Then if you look at your electricity bill, the amount of electricity that you used in a month, which is your one billing cycle, is reported in kilowatt hour. This is the conversion between kilowatt hour and joule. And again, you don't need to know the conversion values at all, but you have to be able to convert it, okay? But you don't need to know the values or memorize them. Now let's talk about endothermic and exothermic reactions. These are the energy that involved in different types of reaction. Then we have endothermic and exothermic reactions. Then what's an endothermic reaction? It's when the system absorbs energy. The change in the energy of the system, which we call it delta H, is always positive. The example is photosynthesis. Okay? Then photosynthesis, the change in the energy of the system is positive. That means the system absorbs the energy. Okay? Then if you look at this example, if you think about the green leaf, okay, then the green leaf takes the carbon dioxide from the air, liquid water from the air, and the heat from the sun. That's the heat from the sun, and it produces sugar or glucose. Okay, your food. Okay, this is an example of endothermic reaction. As you could see, the system is absorbing the energy. Okay, that's why the delta H, or the change in the energy of the system, is positive. This is an example of endothermic reaction. Again, you don't need to be able to know the example at all or write this equation at all, but just know the example. Photosynthesis is an example of endothermic reaction because the system is absorbing the energy to make glucose or sugar or the food. This is the graph for endothermic reactions. As you could see, the energy is increasing. That's why the arrow is going upward. The reactants are at a lower energy level. Whereas the products are at higher energy level. Then as you could see, the energy increases from the bottom to top. Okay, that's why the reactants are at a lower energy level and products are at a higher energy level. And the energy absorbed, the direction, which is this blue, light blue arrow, it goes always from the reactant and to products. And since it's an endothermic reaction, the delta H, which is the change in energy, is positive. Okay, you see, it's a positive number. And as I told you guys in previous slide, photosynthesis is one of the examples of endothermic reactions because in the reactant side, as you could see here, the system is absorbing energy. Okay, that makes the energy of the system to be positive. Okay, that's what it means by the endothermic reactions. Okay, the energy of the system is positive, the change in the energy delta H. Now let's talk about exothermic reactions. It's the complete reverse of endothermic reaction. Now in exothermic reaction, the system releases the energy. The change in energy or delta H is negative. The example is respiration. If you touch your exhale, if you haw on the palm of your hand and feel it, it's hot. Okay, not like hot body temperature. Okay, that means the system is releasing the energy. Okay, that's why the delta H is on the product side. Okay, then respiration, you use the sugar or the food that you eat and the oxygen from the air, and it produces carbon dioxide and water. And since it's an exothermic reaction, the change in heat, or heat, let's call it just heat, is right here. Okay, as I told you, the example is respiration. If you on the palm of your hand, your exhale, you see its body temperature, it's warm. That's an indication of releasing the energy. Okay, now how does the graph look like? For exothermic reaction, then this arrow is going upward, which is positive upward. Then unlike endothermic reactions, now reactants are at higher energy level. Higher energy level. And as you could see, the products are at lower energy level. And as you could see, the change in the energy, which is delta H, which is negative, is downward. Remember, it always goes from the reactant to product. It's this red arrow that goes from the reactant side to the product side. And as you could see, it's negative. It's less than 0, as I indicated here, which means the system releases the energy. Then these are the differences between endo and exothermic reactions. One more time, endothermic reactions, endothermic reactions, a system absorbs the energy, whereas for exothermic reaction, the system releases the energy. In an endothermic reaction, the change in energy, which is delta H, is positive, whereas for exothermic reaction, it's negative. The example of endothermic reaction, like photosynthesis. For exothermic reaction, respirations. Also, in an endothermic reactions, products are at a higher energy level, whereas in comparison to reactants, whereas for exothermic reactions, reactants are at a higher energy level. Okay, these are the differences between endothermic and exothermic reactions, which you need to be able to name couple if I ask you, or realize the graphs and the difference and how it's drawn, so that you look at it and you could fill in the spots if you need to. Now let's talk about heat. Heat is a form of energy, right? It's actually the transfer or exchange of thermal energy. Okay, what causes heat is a difference in temperature. Okay, respiration is a form of heat. You know, your exhale, right? It releases the energy. Okay, it's an exchange of energy. Okay, if you go outside in a really cold winter night, if you look at your exhale, you will actually see it. Okay, why do you see it? Because your body temperature is warmer than outside temperature. That's why your exhale, you will see it in terms of water vapors. Okay, that's an example of exchange of energy. Okay, all right. Another example is when you put an ice cube in a warm water. Okay, then that's my, let me make that bigger because I need that space. That's our warm water, which is at a higher temperature. Now I'm gonna put the ice cube, that's our ice cube, into this warm water. You will see the transfer of heat. The heat always transfers from hotter object to a cooler object. That's the transfer of heat. Okay, it always goes from hotter object to cooler object. Then as you could see here, water is at a higher temperature than ice, right? Because we've told you guys it's a cup of warm water. Then we're gonna have a transfer of heat. Then it goes from water to ice cube, right? Then these teeny tiny arrows, it's the transfer of heat, okay, which goes from water to ice cube. And at some point, after a while, it melts the ice cube completely, okay? Then the key for you guys to know is heat transfers from hotter object to cooler objects. That's the transfer of heat, okay? Like this example that I told you guys. Now, what is heat capacity? Heat capacity is the amount of heat or energy, okay? Heat is a form of energy. Then you could say the amount of heat or energy. It doesn't matter, okay? Amount of heat or energy, and it's the unit is in joules because heat is a form of energy, needed to change the temperature of a specific amount of substance by 1 degree Celsius. Then that specific amount of substance, it's really important, okay? That specific amount of substance is very important. By specific amount, we usually talk about the mass, okay? The mass of the substance. Then by definition, heat capacity is the amount of energy or heat required to change the temperature of a specific amount of substance by 1 degree Celsius. This is the definition of heat capacity. Now, what's the definition of specific heat capacity? Very different, very similar, the names. One is heat capacity, the other one is a specific heat capacity. Then specific heat capacity is when we give unit, okay, to that amount. Give it a unit of grams, okay, that becomes specific heat capacity. Then when we were talking about the definition of, heat capacity, we just said given amount of substance, okay? That's for heat capacity. But for specific heat capacity, we give a name to that specific amount, okay? And that's in grams, okay? That becomes specific heat capacity. That's the difference, okay? The unit for specific heat capacity is joules per gram degree Celsius, okay? Specific heat capacities are unique for each substance. This table right here, okay, table 3.4, shows the sum of the values for some of the substances. You don't need to memorize this table at all. If you need it, you will always be provided with it. But just keep in mind that these values are for specific heat capacity when we give a name or a unit to that specific amount, and that is grams, okay? And this is the difference between heat capacity and specific heat capacity. Now let's talk about energy calculations involving specific heat capacity. Then in order to calculate the heat, we multiply the mass of a substance by a specific heat capacity times change in temperature. That's how the heat is calculated, okay? Which is this equation, okay? This equation will always be given to you guys if you need it. You don't need to memorize it, okay? We will give it to you guys. Then here, Q is heat, right? The unit for heat is in joules. Mass is in grams. Change in temperature is in degree Celsius. And the unit for a specific heat capacity, as I explained in the previous slide, will be joules per gram degree Celsius. Okay? Then specific heat capacity is each substance has its own unique value. That's why when you are using this calculation, you have to make sure that the unit for heat is in joule, the unit for mass is in gram, and the unit for change in temperature, delta T, is in degrees Celsius. If it's not any of these three numbers, you have to do the conversion. Okay, it's very important that you have to keep that in mind. Okay, so we keep the unit for specific heat capacity as is. It's always joule per gram degree Celsius. But for the other three, you need to change it if it does not matches the unit for specific heat capacity. Okay. All right. And as you can see here, delta T is the change in temperature, and delta T is usually T2 minus T1. Okay. And again, when you are doing the subtraction, make sure the unit is in degree Celsius. If not, you need to convert it. You cannot subtract two numbers of different units. And then you have to follow the decimal rule because we are subtracting numbers. Okay? Do not forget that. All right. Let's do an example. We're going to do two examples for specific heat capacity. Then let's do the first one. Then for the first one, what you have, you have the energy, or Q, is in kilojoule. Okay. You have the mass. This is the mass, which is in grams. You were given the specific heat capacity. You do know the initial temperature. Okay. What you need to know the final temperature. Okay. Remember what I told you guys, you want to make sure the unit for heat, temperature, and mass matches the unit for specific heat capacity, or C. Then for temperature does, it's already in degrees Celsius. Okay. Then that's T initial, or T1. The mass does, it's already in 500 grams. The only one that doesn't is the energy, or the heat, which is in kilojoule. You have to convert it to joule. Okay. Then what we're gonna do, we're gonna do a little conversion. We're gonna set up the table so that the kilojoule is gonna cancel out and you end up with joules, right? Then 1 kilojoule is 1000 joule. Okay. Then I set up my equation so that the kilojoule is gonna cancel out. Okay. And then you're gonna end up with 40 times 10 to the power of 3 joules. Now that I converted my heat from kilojoule to joule, now we could use the equation, which is Q equal to mc delta T. Okay. Then we want to find T final, right? But you know that change in temperature, as I told you in the previous slide, is T final minus T initial, or T2 minus T1, same thing. Then this is the one I want to find. And what I'm going to do, using the heat equation, specific heat capacity equation, Q equal mc delta T, I will find delta T. Once I find delta T, I have T initial, I could find T final. Okay. Then delta T will be equal to Q over m times C, which is equal to Q, which is 40 times 10 to the power of 3 joules, divided by m, which is 500 gram, times 4.184. Okay. Then when you plug in all these numbers and you solve for it, let me plug it on my calculator. What do I get? Four is that one. It's 40 to the power of 3 divided by this number. I will get 19.1205 degrees Celsius. Okay, that's the number I got. Now I have to take care of the sig fig, right? Then this number up here is 3 sig fig. This number is 4 sig fig, and this number is 4 sig fig. All right, then between 3, 4, we use 3, which is gonna be your dotted line, which is gonna be 19.1 degrees Celsius. This is change in temperature. Okay, then from here, change in temperature. Now I'm gonna use delta T, which is T final minus T initial. From here, T final is delta T plus T initial, right? Which is gonna be 19.1 degrees Celsius plus 10 degrees Celsius, which is gonna be 29.1 degrees Celsius. This will be your final temperature. Okay, that's how we found the final temperature. One thing that you want to again keep in mind is that the unit for initial temperature matches the unit for change in temperature. Again, if it does not, make sure that it does. Okay, you have to follow the sig fig and everything. For the second part, when we are adding change in temperature to initial temperature, we go by decimal rule. Okay, this number is 1 decimal place, that one is 1 decimal place. That's why my answer was 1 decimal place. Okay, all right. Let's do another example. All right, in this example, we have a metal with a mass of 43.0 grams. Its initial temperature is 100.0 degrees Celsius, and that piece of metal was added to a 38.0 grams of water with this specific heat capacity, and the water's initial temperature is 23.72 degrees Celsius. You are told that the final temperature of water and the metal is the same and is equal to 29.33. The question asks you to calculate the specific heat capacity of the metal. Okay, then the first thing that I'm gonna do, I'm gonna write, that's how I solve problems. Then I will write down everything that's given, which usually help me much better in order to solve complex problems. Okay, then what I'm gonna do, as I just told you guys, I'm gonna write all the given values for metal. Then we know the mass of the metal, which is 43.0 grams. We know the initial temperature of the metal, T initial of the metal, which is 100 degrees Celsius. Okay. We also know the final temperature of the metal. Remember, the initial and the final temperature of water and metal are the same, and it's equal to 29.33 degrees Celsius. These are the information that I know for metal. Okay, now let's do the same thing for water. This is metal. This is water. Okay, then the mass of water, which is given to us, W stands for water, 38.0 grams. The initial water temperature is 23.72. The final water temperature, which is the same as the final water temperature for metal, which is 29.33 degrees Celsius. And we also know the specific heat capacity of water, which is 4.184 joules per gram degrees Celsius. Then what we need to calculate, we need to calculate the specific heat capacity of the metal. This one is the unknown. Okay, now let's draw a diagram and to see it, what's happening. Okay, then this is my container. I have this large container. Okay, and it's filled with water. Okay, it has water. All right, it has water, and the water temperature, the initial water temperature, is 23.72 degrees Celsius, right? Let's make it a little bit smaller, the arrow. Okay, this is water. Okay, now we dropped a piece of metal. That's the metal in the water. Okay, this is the metal, and its initial temperature is given to be 100 degrees Celsius. If you recall a couple of slides ago, what I told you guys, heat is a source of energy and it transfers, right? It always goes from the hotter object to a cooler object. That's the transfer of heat. Always from hotter object to a cooler object. Okay? That's a fact that you have to know. Okay? Now look at the metal and the water. The temperature for metal is 100 degrees Celsius. The temperature for water is 23.72 degrees Celsius. Which one of these two have a higher temperature? Then the initial temperature of metal is much higher than the initial temperature for water. What that means is that the heat transfers from metal to water. Okay, that's what happens. Okay, which is Q. Okay, we have a transfer of heat from the hotter object, which is the metal, to a cooler object, which is the metal, water. And this keeps continuing till at some point the water and the metal reach the same temperature, which is given to us. It's the final temperature, which will be 29.33. Okay? One thing that you want to know, and you will figure out, is that the metal is losing its heat, its energy, and it's giving it to water, right? Because the transfer of energy or the transfer of heat is from metal to water. Then the metal, it's losing the temperature or losing its heat, and it's giving it to the water. That means water is gaining it. Okay? Then if the water is gaining the heat, okay, its heat or Q is positive. Okay? And at some point, these two are gonna have the same temperature, right? For the metal, since it's losing the heat, okay, its heat is gonna be negative. Okay. And these two are important fact that you want to know. Then since water is gaining the heat, its heat is positive. That's why I put positive Q double. Whereas for the metal, it's losing it. It's negative. And at some point, which is the final temperature point, they will have the same energy. Then we're going to use this concept and we're going to solve for specific heat capacity of the metal. Okay, then what I just told you guys, at some point they're gonna have the same temperature. We've been told. What that means is that their Q, it's gonna be the same. Okay, then at some point the Q for water is gonna be the Q for metal. But you have to keep in mind, the Q for water sorry. It's positive. The Q for metal is negative, and you have to plug it in. Why it's positive for water? It's getting the temperature or getting the heat from metal. Why for metal it's negative? Because it's losing the heat. Okay, all right. Then for water is positive, for metal is negative. All right, now let's put in the rest of the formula. Okay, now from here you could say plus, what is Q equal to? Remember, Q is mc delta T. Let's rewrite it for water and for metal. Then for water, it's plus mass of water times specific heat capacity of water times delta T for water, right? Which is equal to negative mass of metal times the specific heat capacity of metal times change in temperature for metal. Okay. Then we do know the mass of water. We do know the specific heat capacity of water. You could easily find the change in temperature of water. We do know the mass of metal. We easily could calculate the change in temperature for metal. And now that we have all the unknowns, we could easily calculate the specific heat capacity of metal. Okay. All right. Okay. Now let's find the change in temperature for metal and for water. And it's going to be T final minus T initial for water. Okay. T final is given to us. It's 23.72 minus the initial for water. Oh, sorry, I made a mistake. Okay, this was the initial. The final is 29.33 actually. 29.33 degrees Celsius minus 23.72 degrees Celsius. These are what they were given to us, you see. Okay, then before doing the subtraction, make sure T final and T initial have the same unit, and they do have the same unit. If they don't have the same unit, you have to convert the unit so that they are the same, and then you could subtract the numbers. But since they are the same number, when we subtract the two numbers, you'll get 5.61 degrees Celsius. Okay, we subtracted, we have to take care of the sig fig. Let me rewrite this one. Okay, since we are subtracting, we go by decimal rule. Okay, then every digit 0 or non-zero will be counted after the decimal. And this is 2 decimal place. This number is also 2 decimal place, and your answer has to be 2 decimal place, which already is 2 decimal place. Then you didn't need to do anything. Now let's do the same thing to find the delta T for the metal, which is the T final for the metal minus T initial for the metal. Then the T final for the metal is given is 29.33 degrees Celsius minus the T initial for the metal, which is 100 degrees Celsius. Then when you do subtract these numbers, you have to pay attention. Here we are subtracting a larger number from a smaller number from a larger number. Then your final number will be a negative number, and it's going to be 70.67 degrees Celsius. Okay, now we take care of the decimal or the sig fig. We are subtracting again by decimal rule. This is 2 decimal place. This number is only 1 decimal place. Okay, then between 2 and 1 we use the smallest number, which is 1, which is here. That's why you need to do a dotted line. That makes it 70.7 degrees Celsius, which makes our final answer to be 1 decimal place. Okay, now we do know the change in temperature for each, for water and for metal. Then what we're gonna do, we're gonna use this equation here, this equation, and we're gonna plug in the numbers. Okay, I'm gonna plug in all these numbers and I'm gonna solve for it. All right, now let's do it. Let's continue with it. The mass for water is 38 grams, then positive 38.0 grams times 4.184 joules per gram degree Celsius times delta T, which I calculated it, which is 5.61 degrees Celsius, is equal to negative Q, which is negative Q for metal, which is negative. The mass of metal is 43 grams times the specific heat capacity of the metal times the delta T, the change in the temperature for metal, which we just calculated it, and it was minus 70.7 degrees Celsius. You could use the rounded, you could use the unrounded, it doesn't matter. For me, some instructor ask you to use the unrounded number because it's more accurate. Okay, now then what you want to do, you want to solve for the specific heat capacity for the metal. Okay, then it's going to be 38.0 times 4.184 times 5.61 divided by times, all right, the negative times negative will be a positive number, right? Okay, then the negative 43 grams times negative 70.7 degrees Celsius will be a positive number. Okay, then if you solve the specific heat capacity for the metal, it's going to be 0.2935 joules per gram degree Celsius. Okay, now we have to take care of the sig fig. Okay, this number is 3 sig fig. Since we are multiplying and dividing, we go by sig fig rule. Okay, this number is 4 sig fig. 5.61 is 3 sig fig. 43.0 is 3 sig fig. And 70.7 is also 3 sig fig. Then between 3 and 4, we go by 3. Remember, the 0 at the beginning of a number is not significant. It's not going to be counted. Then it's going to be 1, 2, 3. That's where you put your dotted line here. Okay? And the specific heat capacity for metal. Since after the dotted line we have a 5, then 3 will be rounded up by 1. 0.294 joule per gram degree Celsius. Okay, this is the answer for this problem. Then, as I mentioned you earlier on, this is a complex problem. That's why it's really a good idea that you write down everything that's given. Okay, and you draw a little picture as I did here. Then when you draw the picture, you write down all the given ones. It helps you a lot better to do calculations. That's how I always solve problems. whether it's an easy one or it's a difficult one, and write everything down. It's gonna help you a lot. Okay. And then once I know what's happening, we did know that the metal is at a higher temperature than the water. That's why the metal starts losing the heat to water. That's why the heat for water, since it's getting the heat, it's positive. For metal will be negative. And at some point, the temperature or the final temperature for the metal and the water will be the same. Then at this point, the heat for both of them will be the same. Then knowing this fact and knowing all the known variables, I set up the equations and I solved the delta T for each metal and water. Remember, the final is the same, we are told it's the same. Then once I know the change in the temperature for the metal and the water, I know the mass of water, I know the mass of metal, we also know the specific heat capacity of the water. Then knowing all of these factors, I calculated the specific heat capacity of the metal. This is the end of chapter 3.